Hey everyone, and welcome back to the channel. In today's video, we're going to be talking about topological sorting. So, what is topological sorting? So, topological sorting is the linear ordering of vertices such that if there is an edge between U and V, U appears before V in that ordering. So, what I mean by that is that let's say we have a graph like this over here. Okay. So if I have a graph like this over here and I want to sort the, vertices in a manner, right? So we need to sort it in such a manner that the vertex, if that there is an edge between U and V, let's say there's an edge between 5 and 0. So 5 should appear before 0 in that ordering. So that is topological sorting. So to give you an example, let's say if I write 5, 4, 2, 3, 1, 0. Right. So as you can see over here, there's an edge between 5 and 0. So let's say this is U and this is V. Right. So you can see that U needs to appear before V in that ordering. So in this case, U does appear before V. Right. Now let's take a case over here. This is 0. 4 is pointing to 0. Right. So there's an edge from 4 to 0. Right. So if there's an edge between 4 to 0, you can see that U and this is V. So 4 should appear before 0 in that ordering. Again, let's say this is U and 1 is V, since 4 is pointing to 1, right? So 4 should appear before 1 in the ordering. It does happen. We have 3 and 1. This is U, this is V. So 3 should appear before 1. It is happening. 2 is U and 3 is V. So 2 needs to appear before 3. So 2 is appearing before 3 in that ordering, and 5 and 2. So 5 should appear before 2 in the ordering. Right. So this is basically what topological sorting is. Right. So if you see this order over here, this is it's sorted in a topological manner. Right. So basically, you need if there's an edge between two vertices, right, and let's say five is the vertex. There is a five is pointing to zero, right? So there's an edge from five to zero, right? So five will be your U and zero will be your V. So this means that U, which is five, should appear in the ordering before V. This is what basically topological sorting is, right? Now, what you also need to know that about topological sorting is that topological sorting only happens in DAGs, right? It only happens in DAGs. Now, what are DAGs? DAGs are basically directed acyclic graphs. ACYCLIC graphs, right? Which basically means that graphs which have directed graphs which don't have any cycles, right? These are what directed DAGs are, right? Now, why does topological sorting only happens in DAGs? Let me just show you with an example over here, right? So let's say if we have a graph something like this, we have a 0 pointing to a 1, we have 1 pointing to 2, 2 pointing to 3, and 3 pointing to 0, right? So if you see over here, it has a cycle, right? 0 pointing to 1, 1 pointing to 2, 2 pointing to 3, and 3 pointing to 0. This is a cycle. Now what would happen over here? So if I make the adjacency matrix of this, right? So what would we have here? We would have 1. In 1 we would have 2. In 2, what you would have? You would have 3. And in 3, what you would have? You would have 0. Now what would happen over here is that if you try to find the topological sorting of this, right? Let's say this is U and this is V, right? Because U is directing, we have a edge from U to V, right? So if we have an edge from U to V, what you can say is that U should appear before V, so 0 should come before 1 in our ordering, right? Now there's a node from 1 to 2, which means that this is U and this is V, right? Which means that 1 should appear before 2 in the ordering. So up till now it's fine, right? 1 can appear before 2 also, like this, something like this in the ordering. Now if we have U and V, right, which means that 2 is pointing to 3, which means that 2 should appear before 3 in the ordering. Again, this is still fine because this you can have, a sorting like this. But the problem comes over here when you have U and V like this. And if you want to, in this case, you want 3 before 0, but you can't have 3 before 0 because 0 needs to be before 1, right? But 1 needs to be before 2 and 2 needs to be before 3, right? But 3 needs to be before 0. So you need 3 over here, but also you need 2 over here, which should be before this. But no, you can't have that because 2 is dependent on 1, which is dependent on 0. So basically, what my point is that you can't have topological sorting in DAGs just because there will be a cyclic dependency. Okay, this is the only reason why you can't have topological sorting in DAGs, right? So this is what the whole thing is, right? Now, how do you find the topological sort of a graph? Right, let's make a DAG again. So we have 0, we have 5, we have 4, we have 1, we have 3, and we have 2, right? Now, how do you find the topological sorting of this graph? Let me just write the adjacency matrix of this once. So if we can have something like this. 1 has nothing, 2 is pointing to 3, 3 is pointing to 1, 4 is pointing to 0 and 1. Okay, let me just do this. Now, 4 is pointing to 0 and 1, and 5 is pointing to 0 and 2. Right. So this is what our adjacency matrix looks like. Now, how are we going to solve this? Right. The way to find the topological sorting is, let's just solve it first. Then we'll understand what we're doing over here. So to solve this problem, what we'll do is first we'll create a visited matrix, visited array. Sorry, not matrix. What would this visited array have? We would have we'll store all our vertices over here. Keep a visited array for all the vertices. So this is for vertices 0, 1, 2, 3, 4, and 5. Right? All of them would not be visited. So we'll keep all of them equal to 0 right now. Okay. Now, what else we're also going to keep is we're going to keep a stack. Okay. We're going to keep a stack, and you'll understand why we're using a stack in just a minute. Okay, let's go down a bit. Now, what we'll do in the question is, okay, this is the pen, right? Okay, so what we'll do, we can since we're going to be using DFS in this way. For this method we'll be using DFS. Okay, this method is done using DFS. So in DFS, as you know, you can start with any node, right? So let's just say we're going to start with the very first node, which is node 0, right? So if we do a DFS on node 0, what we see is that DFS 0 does not have any nodes cited as adjacency list. Right. So 0 has only nodes coming to it and doesn't have any nodes going from it. Okay. So basically, if it doesn't have any nodes in the agency list, we can just add it to the stack. Right. Let's say we're adding it to the stack over here. Cool. Now, since we're done with 0, and we'll also mark 0 as visited. Okay. Now after this, right? Okay. Let me just take a eraser. Yeah. Okay. Now since 0 is done, now we go to 1. Okay. Now we perform a DFS of 1. We see that again 1 does not have any elements on its adjacency list. We'll just make this 0, make it visited, and add 1 to the stack. Okay. Now you know what, I can do it from here also, right? Yeah. Now, okay. Since 1 and 0 are visited, now we go to 2. Right. Now once we go to 2, you see that we mark 2 as visited. Okay. 2 is now visited. But as okay, what is this? Yeah. Now as we mark 2 visited, you can see that 2 has 3 in its adjacency list. Right. So we won't add to the stack, right? Because the DFS call of 2 isn't completed. So we go to 3. Right. We go to 3. We do a DFS on 3. Right. Now when we do a DFS on 3, we make 3 visited. Right. Now when we make 3 visited, we see what elements do we have in its adjacency list. Okay, now whatever we're doing is just a standard DFS calls, guys. Okay, it's a basic method of how we perform a DFS. Nothing special. Okay, and the only thing different what we're doing is adding to the stack. Okay, and how we're adding the stack, we're just saying when the DFS calls of any value gets completed, we're adding to the stack. So in case of 0 and 1, the DFS calls were completed, so we just added to the stack. In case of 2, it didn't get completed, right? We went from 2 to 3, so we have a DFS call over here, right? Now when we go to 3, we see that 3 has 1 in its agency list. Now, since 3 has 1 in its agency list, but 1 is also visited, as you can see from over here, 1 is visited, right? Which means that we can't go from 3 to 1, right? Since we can't go from 3 to 1, the DFS call of 3 is now completed, and we can add 3 to the stack. Right. Now, since three is calls are complete, we go back to two. We see that we only have threes in its adjacency list. So the calls of two are also completed because three is also visited, and we went to three and we came back as well. So the calls of three is also complete. Two is also complete. We add two to the stack. Now, once they are added, now what we'll do is we'll okay. So let me just rub this. Yeah, what we'll do is we'll perform a DFS on four. Right. We'll perform a DFS on four. We'll see that we have zero and one. Right. When we have zero and one, we'll see that zero is visited. Right. So we won't perform a DFS call on it, and one is also visited. So we won't perform a DFS call on it. Since both of them are visited, the four calls of fours are finished. So we add DFS. We add four to the stack because the DFS calls of it is finished. Now we also mark this as visited. Now we go to 5. We see that 5 has 0 and 2. Both 0 and 2 are visited, right? And the DFS calls of 5 is also completed. So we add 5 to the stack. Right. Now, after adding all the elements to the stack, what you'll do is pop each element from the top of the stack one by one. Right. So as you start popping, right, you'll get 5, 4, 2, 3, 1, and 0. Right. After popping all the elements from the stack from the top, right, you'll get this, and this is what the sorted topological sorting is. Right, this segment or this sorry what this sequence which you get over here is the topological sorting of this sequence of this graph. All right, so this is how you perform a topological sort. Now what the intuition behind this is that, let's say you have a graph like this: 0, 1, 2, 3, we have 4, and we have 5. Right. So what we're doing is we see that zero is dependent on one is dependent on two is dependent on three is dependent on four and five. Right. So what we're doing over here is we're going from zero to one to two to three to four. Either we can go to four, either we can go to five. It doesn't really make any matter in this case. Right. But what is happening over here is what we can have as a sequence in this graph is either this or either this. Right. Now, in both the cases, as you see, is that I think this three is, I think, pretty much obvious why it's this sequence over here. But in this three, because three has to come before four, right? We are writing it before four, but four is not dependent on anyone. So you can write four like this and five like this as well. And in this case, when 3 is dependent on 5, right, you can write 5 first and 4 later. It doesn't really matter because these two are not dependent on each other, right? So this is also one sequence what we can get. So there can be multiple sequences of orders you can get, but it doesn't really matter what sequence you need to give for the topological. Any one sequence which you give as an output is fine. Now, what is the intuition behind it? The intuition behind it is why we're adding to the stack, right? What we're doing is, as and when we complete the DFS calls, we're adding to the stack. Now, what happens over here is that, as you see over here, 0 is dependent on 1 is dependent on 2 is dependent on 3 is dependent on 4 is dependent on 5. Right. Now, all these elements are dependent on each other except for 4 and 5. Right. 3 is dependent on both of them. Now, what will happen is, as I finish my DFS call of 5, right? As I finish my DFS call of 5, okay, you know what? Let me just write in a proper way. You can see that 0 is dependent on 1 is dependent on 2 has to be before 3 has to be before 4 and 5. Right. So as and when I perform my DFS, right, I see that I go from 0, I go to 1 in its adjacency list, and I keep on, filling my visited array as well. This is 1. This will be 1 because I go to 1. 2, 0, 1, 2. 2 will also become 1. Now from 2 I go to 3. 3 will become 1. From 3 I go to 4 and 5. First I'll go to 4. Right. Since I go to 4, I see that 4 is not visited, right? I add this to my list. And when I add this to my list, I see that my DFS calls of 4 are now completed, right? Because I don't have anything in my 4s. This is 5. They don't have anything, right? Since they don't have anything, the DFS calls of 4 is going to be completed first, right? Now, since DFS call of 4 is going to be finished first, I can write my 4 over here like this, right? I can write my 4 like this. I can add 4 to my stack very first. Now, since 4 is added to the stack, go to 5. I add 5 to my stack. Right. 5 is also, there's nothing present in it, so 5 is also getting added to the stack. So you see over here 4 is added, then 5 is added, right? Now since 3 is going 3 is completed, 3 gets added to the stack. Now since 3 is completed, 2 gets added to the stack. What my point over here is, what we're doing is that as and when the calls of the DFS are getting completed, right, this means that all the elements before over here, right, so the element which I add to the stack basically means that there is everything ahead of it is already sorted, or is has already been added to the stack, right? And there's no more DFS calls we need to do ahead of it, so that we need to add it again. Okay. So again, let me just explain it again. What I mean by that is, as let's say my three's DFS call is completed, right? And I add it to the stack over here. So right now it's 4, 5, and 3 like this. So when I add 3 to my stack, I know that this DFS call of 3 is completed. That's why I'm adding to the stack. But this also means that everything ahead, like everything dependent on 3, everything which 3 is dependent on, let's say 4 and 5, are already added to the stack, and everything ahead of it, this whole portion is going to be sorted, added to the stack in a sorted manner, because all the DFS calls of 3 is completed, right? So when I add 2 to my stack, everything ahead of 2, all these things are going to be added in a sorted manner, like 4 which was dependent on 3, 5 which was 3 which was dependent on 4, and 5 both are added. 3 which was dependent on 2 which was dependent on 3 is also added. Then we add 2, the DFS calls of 2 is complete, which means that all the elements 2 was dependent on gets sorted, added in the stack in a sorted manner, right? All the elements ahead of it, right? The similarly goes for 1. All the elements ahead of 1 are getting added to the stack in a sorted manner, right? And all the elements before 0 are getting added to the stack in a sorted manner, right? So when we add, since all the DFS calls of these elements are completed, the 0 over here, the very last one, when it's added, you see that when you start popping the elements one by one from the top of the stack like this: 0, 1, 2, 3, 5, and 4, right? This sequence which you will get after popping all the elements from the stack is basically your topological sort. Because if you see over here, okay, so if you see over here, 0, 1, 2, 3, 4, 5, right? 5, yeah. So if you see over here, so this was U, this is V. So U should be before V. So 0, then 1, right? Then U, then V, 1, and then 2. U, V, this should be 2, then 3. U, V, U should be before 4, and U, V, this should be before 5, right? In this case, if you write 5 before 4 in the adjacency list, you'll get this order over here. But if you write 4 before 5, you would have gotten 5 and 4 like this. So it doesn't really matter. This you can give any sorted output, topologically sorted output, any one sequence. That is fine. But this is what the main intuition behind the problem is, guys. That as and when your DFS calls get completed, right? As and when an element's DFS call is completed, that element is basic can get added to the stack, which means that that gets added to the stack in a sorted manner. Right. So everything in its adjacency list would already be added before it. Right. So let's say if 3 has 4 and 5 in its adjacency list, both of them are added to the stack before it, and they both are already sorted. Right. If you think about logic, both of them are added in a sorted manner for 3, so that we get a topological sort. Right. So when we add 3 since when 3's DFS calls is completed, we add 3 to the stack, and you see that for 2, all the elements which were ahead of it, like 3, and 3 had 4 and 5 in its adjacency list, all of them were added in a topologically sorted manner, so that the sequence is maintained. So the main intuition behind this question is to just add the elements as the DFS calls is completed in the stack, and once all of the elements are added, just start popping the elements from the top. As in what happens in a stack, all the elements that are stacked on top get popped first, and when they get popped first, you get a proper sequence of a topological sort. So this is basically what the topological sorting problem is, guys, and this is how you solve the problem. Okay. So uh, let me just show you how to code this out once. Okay. So to code this, right, so this is what we're doing, guys. Yeah. So this is what we're doing, guys. So this is what our adjacency list. We're going to solve it using the DFS method. What we'll do is we'll maintain a visited array. right? We'll maintain a visited array. All the elements in the array will have a value of 0, right? We'll keep maintain a stack for us, right? After maintaining a stack, let's close this out for now. After maintaining a stack, what we'll do is we'll loop through the list, right? We'll check if the element is visited or not, if the vertex is visited or not. If the vertex is not visited, what we'll do is we'll perform a DFS on it. Right? When we perform a DFS on it, we'll pass in the value I. In this case, let's say we are passing in 0, because this is the very first value of the this 0 gets passed, right? Since 0 gets passed, we perform you know we perform a DFS on it. We pass it over here. The visited of this node gets equal to 1. So let's say visited equal to 1, then 0, then 0, 0, 0, right? So, this is the case when 0 is passed, right? This is what a visited array will look like. Now, in our visited array, since for j in adjacency list of node, there's nothing present in the adjacency list of 0, right? What we'll do is we don't go inside this if statement, and we'll just check if it is added to the stack or not. If it is not added to the stack, what we'll do is we'll just add the element to the stack like this. 0 gets added to the stack. Okay. Now, since 0 is added, this DFS call is completed. We go back to this statement over here for I. Now we go for 1, right? When we go for 1, in this case, now this is 1. Yeah, 1. Right? We check if visited of I is equal to 0. It is 0. We pass 1, visited an adjacency list over here. Right? We make this equal to 1. We check in one's adjacency list. We don't have any element, so we don't go inside this if statement. We just check if it's present in the stack. It's not present in the stack. We just add it to the stack. Right? This DFS call for 1 is now completed. Now we go for 2. Now, in case of 2, what we're doing is we're checking if visited of I is equal to 0. Yes, visited of I is equal to 0. We pass 2, visited adjacency list. We make the visited of 2 equal to 1. Right, now we check for the for j in adjacency list of node. We check for 3. Right, so 3 is present in the adjacency list of 2. So we pass 3. We check for 3. If visited of 3 is equal to 0. So yes, visited of 3 is equal to 0. Is equal to 0. So what we do is we perform a DFS call on the of 3, and we pass 3 visited and adjacency list. After passing 3, this gets completed. This gets visited of 3 is equal to 1. We check for visited of 3 is adjacency list. We check for the nodes in the adjacency list of visited of the 3. We have 0 and 1. We only have 1. Right. Since we only have 1, we know that the visited of 1 is equal to is not equal to 0. Right? It's equal to 1. So we don't go perform a DFS call on it. What we do is we just check if 3 is not added to the stack. We just add 3 to the stack now. Right. We just add 3 to the stack, and the DFS call of 3 is now completed. Right. Now the DFS call of 3 is completed. Now we go to the DFS call of 2. Right. When we go to the DFS call of 2, we see that the DFS call is completed. So we check if it's not appended to the stack. We then append it to the stack. Now we add 2. Right. And the DFS call of 2 is now completed. Now, right. Now we check for the DFS call of 3. We check if visited of I is equal to 0. So it's not 0. It's already 1. So we don't perform it on 3. Now we go to 4. In the case of 4, we see that visited is equal to 0. Yes, we perform a DFS on 4, visited an adjacency list. Right, now we see the elements. We make the visited of 4 equal to 1. Now we see the nodes in the adjacency list of 4. We have 0 and 1. Right, now we check the visited of 0. Is the visited of 0 equal to 0? So it is not. It is equal to 1. So we don't perform a DFS call. Again, in case of 1, it is also 1. So we don't perform a DFS call on both of it. And we just check if 4 is not appended to the stack or not. If it is not, we just append it to the stack, and we complete the DFS call for 4. Now, in case of 5, it's pretty much similar. Right, we go to 5 over here. We check for 5 now. In case of 5, if visited of I is equal to 0, it is 0. We pass 5 visited adjacency list. We make the visited of 5 equal to 1. Equal to 1. Now, for in the adjacency list of 5, we have 0 and 2. Now, both of them are visited. So we don't perform a DFS call, and we just check if 5 is passed into the stack or not. If it is, we just pass it like that. If it is not, if we just pass it, add to the stack. Now, after adding to the stack, what we'll do is we'll just start pop each element from the top. So 5, 4, 3, 2, 3, 1, and 0 will be popped from the top. And you can just, in Python, you can also write, because I'm not using a stack, I'm just using an array over here. I can just write it like this. and it'll give me basically what this gives is the reverse order of your stack, or reverse order of your array. If you write it like this, right? And if I write it like this, I'll get my topologically sorted graph. So this is 5, 4, 2, 3, 1, and 0, right? So that's all for today's video, guys. And also, what the time complexity of the code is. The time complexity of the code is O of v plus e, and the space complexity is because we are using a visited array, and a stack is going to be O of n plus n, right? So O basically, which is O of n, right? So this is what the time complexity and space complexity is, guys. And yeah, guys, that's all for today's video. If you like the video, do like, share, and subscribe. Do let me know in the comments what I can do better to teach you all these concepts. And until next time, guys, thanks for watching.